Okay, yeah, so binary trees. Binary trees. And let me switch it. There we go. All right. So what are binary trees? We're going to learn a little bit of tree traversals. I love this stuff. And an incomplete, we're going to look at an incomplete binary tree implementation. And the reason it's going to be incomplete is not because it's a case of left incomplete as an exercise for the student, but more that the topics are a little outside the scope of this course. So they're a little sophisticated. Not that you couldn't do it, it's just we don't want to push it. So a general tree is a tree where each node has any number of children, 0 to many. And an n-ary tree is a tree where it has n children, where like no node has more than that, like that's the max number. But a binary tree is a tree where each node has no more than 2 children, or a 2-ary tree, but we'll always say binary tree. The children, if they exist, are actually called left and right in a binary tree almost always, and so like the direction matters. And in a unary tree, well, we talked about that yesterday, that's basically just a list. So a recursive definition of a binary tree would look something like this. It's either an empty tree or a tree that has a root whose left and right subtrees are also binary trees. And a binary tree, it matters if it's left or right. Yeah, I just said that. So it's positional. So here's an example binary tree. And again, I'm missing my writing thing, but that's okay. So this would be left. This would be right. This would be left. This would be right. This would be left. This would be right. Oh, but there is no left. So left is empty. Left, left, right. See some boops. Can parents only have 2 children? Yes, in a binary tree, parents can have at most 2 children. They could have 1, they could have 0. If they have 0, they're a leaf. If they have 1, well, they're, but is left or right 0, 1? I'm not sure what you mean. Like, would we call them 0 or 1? Is left or right 0 or 1? I'm not, what do you mean? Like binary? No, I see what you're trying to connect it to, like this binary number system. No, they're just left or right. Yeah, we just assign them like left and right. So if you, I mean, imagine implementing this. Imagine implementing like, so you could think of like the linked structures, like the linked lists, for example, the nodes, right? And the node has data and then a next. Well, here we could have data and then a left and then a right, and both left and right are pointers to like binary tree nodes or something. So with list traversals, it's simple, right? I mean, here's a linked structure, and it doesn't need to be a linked structure. Like we could talk about like an array implementation of a list as well. But with these simple linear structures, the order that we traverse things is obvious. You start at the head and then go to the next thing, and then go to the next thing, and then go to the next thing, and you keep doing this until you're out of things. But when it comes to a tree, it gets a little bit different. I mean, okay, and I guess we can get fancy. If we want to get fancy, we could go backwards, I guess. Sure. But in a tree traversal, if I say, like, sure, these things are labeled A, B, C, D, E, F, G, and whatnot, right? But the fact that these are labeled doesn't mean that there's like an ordering. They're just a label. So if I ask, like, if we go here, and I say, what comes after this thing? Well, it's this thing, right? Obviously, because, well, what's next? But here, what comes after A? Well, I mean, we have 2 options. We have left and we have right. So, I mean, it's not really natural to even ask, like, well, what's next? It's, well, we've got 2 options. So what's next kind of depends. So a binary tree, or trees in general, are typically, well, I shouldn't even say typically, a lot of times, although we can make a linear tree, because we saw lists are effectively a unary tree, But these nonlinear structures, we've got a few options on how to traverse this tree. And I'll give you a moment, like actually look, oh, I don't want to say that. Actually look at this tree and take a moment, like I'll give you 30 seconds to think about like how might you traverse this and how else might you traverse it and whatnot. And of course we could play a game where it's like, well, go to A to I to B to G to D. I mean, that's kind of silly. But think of like useful, potential practical ones. And I'll give you a second to do that. And while you do that, I'm going to clicky and clack away over here on another keyboard. Like, hopefully you thought of some things. I mean, we don't need to talk about what Pigby came up with because chances are we're probably going to talk about a couple of them. So there's a pre-order traversal, an in-order traversal, a post-order traversal, and then what we call a level order traversal. And of course, we could have as many other types of traversals as we want, but these are like ones that might have some like practical utility. So we'll start with the pre-order traversal, and here's the rule. Start at the root. Visit the left node, or pardon me. Visit the node, then go to the left child, then the right child. That's it. But we're going to do this recursively. So here's the idea. If the tree is not empty, visit the root and do something. So in our case, we'll just print, right? But I mean, maybe we're doing like a search or something in the tree. But to say that we have visited that node, that tree node, we'll print out whatever the data is. And in our case, it'll be the labels that we have, like A, B, C, D, and whatnot. So if it's not empty, visit the root of this subtree, or maybe it's the full tree. Visit the root node, print out the information. Then do a pre-order traversal on the left subtree. And then once that's done, do a pre-order traversal on the right subtree. And if you're a little worried about like, oh man, recursion again, let's just, like, what does the code say? Remember, there's no silver bullet except this. What does the code say? Do what the code says. So let's start at A. If we do a recursive traversal on A, what do we get? Well, we'll start at A, right? And what does it say? Okay, visit the root node, print. Okay, cool. I'll print out A. So I don't know, A. So we did that bit. Then it says do a pre-order traversal on left. Oh, okay. So now we go to B. And so we do pre-order traversal on B. And it says, oh, okay, well, print out the information here, B. Okay, we printed this out. Then we go to the left. Dude, okay, it's not empty. Print out D. Go to the left. Oh, it's empty, so we do nothing. So we finish that function call, and we're back here again. Because, you know, the thing got popped off the call stack, and we returned to the calling function, which would be when we call recursive pre-order traversal on D. And then once we finish the left sides, which we just did, because there was nothing there, it was empty. We do the pre-order on the right subtree. Okay, so go to H. Oh, I should have checked that. Go to H. We visit H. Okay, print it out. Go to the left. Well, there's nothing there. Go to the right. Nothing there. So now we're done. We are done H, and we can pop it off. So done. So now we're back at D, but now we just finished D's right child's pre-order traversal. So we're done with D completely. Now we're back at B, but we still have to do the right subtree. So we go here, we print out E. We go to the left, nothing there. Go to the right, nothing there. We're done with E. We're done with B now because we finished the right traversal. Now we're back at A. But so now, like, it's like we're at A and we just finished this line and now we need to do this line. So with A, do the pre-order on the left, on the right subtree. So we go here, print out C. Okay. Go to the left, print out F. Okay. Go to the left, print out I. Okay. Go to the left, nothing there. Go to the right, nothing there. We're done. Okay. Now we got to go to the right, nothing there. We're done. We're here. Oh, okay. Go to the right. Okay. Print out G. Okay, go to the left, nothing there. Go to the right, nothing there. We're done. That means we're done C, and that means we're done A. So the pre-order traversal should be A, B, D, H, E, C, F, I, G. Wait, did I do that right? A, B, D, H, A, B, D, H, E, C, F, I, G. E, C, F, I, G. Look at that, I did it right. Hooray. So, any questions about what we just did, though? I mean, okay, here's a slide that's basically showing the steps. 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. But we just did it basically together here. But are there any questions about the pre-order traversal? I'll give you a second if you got any. Well, maybe not. But I think what I'll do, okay, so seeing none, we'll go to the in-order traversal. So, in-order is this. Start at the root, go to the left, then deal with the current, then go to the right. Basically, recursively, if the tree is not empty, do an in-order traversal on the left, then deal with the information, then do an in-order traversal on the right subtree. So looking at this, I'm going to give you a moment to see if you can come up with the ordering yourself, okay? Follow this rule and see if you can get the ordering yourself, okay? I'll give you a moment. And yeah, have a go at it. Okay, hopefully I gave you enough time, but what do we, someone type in the order they got, and we'll see, here, actually, no, don't type in the order, don't type in the order. Let's do it together, and then we'll see how everyone did. So, what are the rules? Okay, so, we're here, but we don't print out anything yet. We do an in order on the left first. Okay, so we're here. Don't do anything yet, do an in order on the left. Okay. Don't do anything, do an in order on the left. Okay, there's nothing here. So now we go back here. Okay. So now we finished the left, so we print out D. Then we go to the right. Then we go to the left, nothing there, print out H. Go to the right, nothing there, return, return. Now we're done D's right, so we're done. We go back here, and now we can print out B. And then we do this on B on the right. Okay, we're here, go to the left, nothing there. Print out E, go to the right, nothing there, return to B. B is now done, we return to A. And so now we just finished this bit, and now we're here. So, print out A. Then we do the in order on the right. So we go to C. All right, don't do anything yet, go to the left, go to the left, go to the left, nothing there, go back, get I, go to the right, nothing there, return. Okay, so now we can print out F. Go to the right, nothing there, return. C. Then go to the right. Now we're at the G. We go to the left, nothing there. Then we can print out G. Then we go to the right, nothing there. We return, we're done. So we got DHBEAIFCG. DHBEAIFCG. Look at that, I was right. Who was right? Raise your hand if you were right. Keep your hand up. I was just kind of confused. Yeah, okay. Not crazy because I just threw it at you. But remember, there's no magic here. It is what does the code say? So it looks like only one person got it right. So very well done, Victoria. But yeah, when in doubt, what does the code say? Like that's what we're gonna do. So we're at a node. We do in order on the left. And then when that's done, I can print out A or deal however I want with this current node. And then do in order on the right. So take a wild guess. What's next? Post order. And I'm willing to bet that you know what the code's gonna look like, or the algorithm's gonna look like. Oh yeah, look at, I even said that. Take a wild guess. So start at the root, go to the left, then the right, then visit the current node. So recursively, if it's not empty, do post order on the left, then do post order on the right, then print out the current node's stuff. So let's see if we can do it. And I'm going to give you a moment again. See if you can follow this one. Now that we've seen two, hopefully you can get this one done. So I'm just going to mute myself here. Okay, what do we think? Actually, no, wait. No. I'm going to do it. I'll do it, and then we'll see. So, we're here. Okay, we got to do post order on the left first. Okay, so we go here. Oh, we got to do post order on the left first. Okay. Post order on the left. Okay, well, there's nothing here, so we're done. Then we do post order on the right. Okay. Go to the left, nothing there. Go to the right, nothing there. Now we can print out H. Then we're done with H, so we finish D's right. I heard a boop. What do we got? What is post order? This is post order right here. Post order is this function that we're defining. It's the recursive function. Post order traversal is the post order traversal by definition. And this is it. Do post on the left, then post on the right, then print out the contents. Was that your question? Because what we're doing right now is post order. That's this algorithm right here. So we finished H's right. There's nothing there because it is empty. It's not empty. So now we finished H's left and then right. Now we can print out H. So now we're done with H. We're back at D. We just finished D's right subtree traversal, so we can print out D. Then we return back to B. So we just finished B's post order traversal. Now we need to do the post order traversal on E. So we're here. We go to the left, nothing there. Go to the right, nothing there. Now we can print out E. We're done with E. We can return. We just finished B's right child's post order traversal. So now we can print out B. Now we're back at A. So in A, we just finished this one. Now we need to do this one. So that's what, we don't print out A yet. So we go to C. Okay, first thing it says to do is do the post order on left, post order on left, post order on left. Well, there's nothing there, so we're done. I's post order on right, nothing there, we're done. So now we can print out the I. Then we return to F, do F's right subtree, nothing there. So we can print out F and we're done F. We return to C. Now at C we need to do the right subtree, so we go to G, nothing there, nothing to the right of G. Now we can print out G. Then we can print out C because we can return to C, deal with the contents. Now we're done C. Now we're back at A. And then because we just finished the post-order traversal on the right subtree, we can now print out A. So let's see if I'm right. HDEBI, HDEBI, FGCA, FGCA. Yay, I was right. So, raise your hand if you were right. Again. 1, 2, 3, 4, 5. Okay, it looks like about 5 people. Okay. So, if it's really throwing you off, remember, what does the code say? But this here shows you the thing that we do. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the first thing here, the H. 11, 12, 13, 14, 15, 16, 17, 18, 19. E, that's the E right here, and so on. Now, notice how similar these traversals are in terms of their algorithm. The only difference is when we deal with the current node. In pre-order, it's before we do any recursive calls. In order, it's in between when we do recursive calls. And in post-order, it's after we do the recursive calls. We are very lucky that we have come up with such appropriate names that basically describe the algorithm. Did I hear a boop? I did not. Did I hear a boop? So doing post order left on a thing, we'll do left with no left means it just doesn't do anything. Well, no, it goes. I mean, effectively, yes, but the algorithm is if the tree is not empty, do this. If the tree is empty, we do nothing. Because this right here is like empty tree. Nothing there. Yeah. So, pre, before, in the middle, in between, and post, after. Remarkably wonderful naming. So if and when, someone stops you on the street and they say, quick, tell me the difference between pre, in, and post, and you can't remember, all you have to do is go, wait, pre. Pre means before, in means in between, and post means after. And you're good to go. Because we know that happens a lot. People stop me on the street all the time asking me how to traverse lists. Or pardon me, trees. So, level order is the funny one. But it's pretty simple. Visit the nodes at each level from left to right. So, I'll give you a minute or two to do this one too. And we'll see if you can get it. All right, hopefully this one's not too bad. So what does it say? Start at the root. Visit the nodes. Okay, so A. Okay, there's no more there. So now we go to the next level. And we see B. And then, C. And then we go to the next level. And then we see, it's D. Followed by E. Followed by F. Followed by G. Whoa, that F went funny. G and then H and then I. Raise your hand if you got this one right. Because this one's not recursive. Let's see. I want to see a lot of hands up. 1, 2, 3, 4, 5 people. All right, well, maybe the other ones just aren't here, or they're not participating. 6 people. All right, cool. So that's the level order traversal, but still caught up thinking about the others. Okay, well, the others are recursive, and if you're having trouble with them, definitely practice them, practice them, practice them, practice them. But they're recursive. This one here isn't recursive. I mean, we could make it. Is there a recursive algorithm for level order traversal? Okay, well, yes, but that doesn't mean it's good. Here's the typical implementation. Start with the root. Add it to the queue. Okay? Well, the queue is not empty. DQ. Deal with the current nodes. Print it. And then in-queue the left child. In-queue the right child. Continue. So, let's go back here and do this. So, no. Let's clear everything here. So, imagine we have a queue. All right? So, I'm going to do this to kind of like represent my queue. First thing I do is I go to the root and in-queue it. Note, right here, this is the queue, not what's printed out. So, now I DQ A, so A is not here anymore. I print it out, and then in-queue A's left child, then I in-queue A's right child. Great. Repeat. DQ B. Print it out. Add its left child. Add its right child. Great, we're done. Now DQ. Oh, we have C. Print it out. In-queue its left child. No. My goodness. In-queue. There we go. And then in-queue the right child. G. Okay, now DQ. Print out the D. Add the left child. Well, there's nothing there. Add the right child. H. Great, we're done. DQ E. Print it out. Add left, nothing there. Add right, nothing there. Okay, we're done with it. Now we go to F. In-queue left. There's the I. In-queue right, nothing there. Wait, oh, pardon me, I skipped printing out F. Big mistake. Okay, now we can DQ G. Add the left, nothing there. Add the right, nothing there. I forgot to print it again. DQ H, print it out. Add the left, nothing there. Add the right, nothing there. DQ I, print it out. Add the left, add the right, nothing there. When the queue is empty, we know we're done. So that is your typical easy implementation of a level order traversal. It makes use of a queue. Pretty cool, eh? All right. Any questions about anything we've seen so far here? See something else here. Okay. Well, no questions. Okay. Yeah. All right. So, and then, great. So, iterative traversal. So, changing the container will change the order of the traversal. So, we just used a queue to do a level order traversal. I'm curious, what would happen in that iterative implementation? What would happen if we go back here and we used a stack? Let's go here and do it. So instead of the queue, let's pretend this is a stack. Erase everything. Is there a hotkey for eraser or anything? Doesn't look like it. Okay. So we've got our stack. So we've got A. Push it on the stack. Take it out. Print it. Jeez, this is going to be a nightmare, but whatever. I'm going to have to deal with it. Okay. Go to the left. Add it. Go to the right. Add it. You know what? I'm actually going to switch the order. I'm actually going to say push the right, then push the left. Just for a little bit of simplicity here. So push the right. So then we have C, then we've got B. Okay, pop. We deal with it. B. And then we're going to have to push B's left and right, but we've removed B. So now we go here. Just going to keep an eye on the time. Oh, we've got plenty of time. So B, we put in the, oh, we do right first. So we do E and then D. Okay, cool. Now pop. All right, print out the D. Get rid of the D. And now we put the left on. Well, there's nothing there. Put the right on. Okay, H. Okay, pop the H. Let's erase it. Put the left on the stack. Nothing there. Put the right on the stack. Oh, pardon me. I should be saying put the right, then the left, because I'm doing it that way. Okay, cool. Pop the next thing. Well, that's E. All right. Okay. And then push the left, push the right, push the left. Okay, nothing there. Cool. Now we pop the C. So we print out the C, and of course, oh no. And then we do that. And then we put the right, which is G, and then the F. Okay, cool. We're done. Then we pop the F, print it out. Then take F's right, push it on the stack. There's nothing there. And then push the left on the stack. That's I. Okay, great. Okay, pop. Well, we got the I, and of course we popped, so let's erase it from the stack. Great. Push the right, push the left. There's nothing there. All right. Well, then I guess we could just pop the G. Great. G. Push the right, push the left. There's nothing there. Stack's empty. No, I'm done. So what do we have here? A, B, D, H, E, C, F, I, G. Anyone, like, which traversal did I actually just do? Pre-order. Is that right? Let's go check the pre-order. In order, pre-order. A, B, D, H, E, C, F, I, G. Was this? No. A, B, D, H, E, C, F, I, G. It looks like it. Huh. And you know what? What do you think would happen if I actually moved this deal with to here, but not with the Q, with the stack? And then I switch the orders here for right and then left. Ugh. But look, right? So what do you think would happen if I just pushed the deal with the current thing here? In order? You know what? Let's do a quick little thought about this. So let's erase everything. So, because I'm curious, maybe there's a little bit more bookkeeping we have to deal with. So we've got A, we push A. Then we pop A, but we don't print anything yet. We push C, then we push A back, maybe? And then B. Interesting. So the stack will obviously let us do the in order, pre-order, or post order. And the reason is because although in the other, like in our recursive algorithms, like one of these right here, here's the post orders recursive. I mean, obviously I didn't make use of a stack data structure. I did not say, okay, C++ create a new stack. But ultimately we did use a stack. We used the system stack because of the features of like call frames that were pushing and popping off the system stack. So how would you change the level order traversal to pre-order? Well, we just spoiled that. So the generative iterative traversal is assume a tree exists, create a container, put root in the container. While the container's not empty, remove from the container, deal with the thing, add children, and so on and so on and so on. Like we just saw. And order these depending on the type of traversal we want. So, Consider we have a binary tree of, and this is important, listen to what n represents here. If we have a binary tree with n nodes, what is the computational complexity of doing our in-order traversal? N. It's not a trick question. If you need to visit each node and print it out, well, how many nodes are there? So a lot of people look at this and go, whoa, hold on. Wasn't it the case that when we did like a recursive function that had 2 recursive calls inside the function, wasn't that the case of like 2 to the n, because for each thing it doubled like the number of calls? And you're right, that was the case, but the difference here is what, and this is so critically important. People get obsessed with the idea of n. Well, what's n? N is the, we've got to be careful about what n represents here. I used n as the number of nodes. What if I used n as like the height of the tree or the depth of the tree, whatever we want to use? Imagine n was the depth. Then how many calls are there? So it really does matter. And in fact, what's the relationship between the number of nodes in a binary tree and the depth of a binary tree? So let's think about this for a second. If we have one node, its depth is 0. If we have, well, let's just 1, 2, 3. If we have 3 nodes, the depth is 1. If we have 1, 2, 3, 4, 5, 6, 7, the depth is clearly 2. If we have 7, 8, 9, 10, 11, 12, 13, 14, 15 is 4. So anyone know what the relationship here is? What's the relationship between 1 and 0, 3, 1, 7, 2, 15, and 4? Something times 2 to the n. So close. So if I did like 2 to the n minus, well, let's see if it's 2 to the n minus 1. So if we 2 to the 1, that equals 1. No, wait, that equals 2. So that's 1? I'm not sure. Okay, so if we do 2 to the 3, well, that's 8. Maybe, what if we do 2, what if we kind of flipped what you were suggesting? So what if we did 2 to the 0? Oh, what do we see here? 2 to the n minus 1 minus 1? All right, well, let's try that. Let's try that. 2 to the n minus 1. So let's erase all. Okay, so shoot, I shouldn't have erased that. So we have 1, 0, 3, 1, 4, 5, 6, 7, 2, 15, 3. Let me put it this way. What do you think comes after 15? Does anyone seem to think it should be like what do we think? 31 maybe? 31. Yeah, 31. So you clearly see the pattern, but how do we describe this pattern? Like, so you clearly see the pattern. How do we describe this pattern in terms of math? What are we seeing here? 2. Well, let's see. So I like the idea of playing with what we saw. So 2 to the n minus 1. So if this is, so 2 to the 0, okay, so 2 to the 0 equals 1, minus 1 equals 0. Okay, so what if we do, okay, 2 to the 2 equals 4. Oh no, that should have been 3. 3 minus 1. No, that can't be right because this would have been 4 minus 1 equals 3, but that, you know, we're looking for 1. So that can't quite be it. What else are we trying here? Times 2 plus 1? 4 times 2 plus 1. I'm not sure. So 2 to the n plus 1 minus 1. Okay, well, let's try that. So 2 to the 2 is equal to 4 minus 1 is equal to 3. Well, we were looking for 0, right? Wait, I thought n was depth. No, n is the number of nodes. So you want to switch that around a little bit. Okay. So you're thinking we should switch it. Okay, that's cool. I like the idea of switching it. So what do we have to do to 0 to get 1? Well, I mean, 2 to the 0 equals 1, right? Is that right? So then we've got 3 here. So 2 to the 2, or pardon me, 2 to the 1 is equal to 2. Well, that's not quite right. Right? So what if it's so what are the numbers representative of? Well, now we've made n. So n was the number of nodes before. But now so we were trying to go from here to here. Now we can just as easily go here to here and just like look for the inverse operation. So now like, we just shifted to try to go from 0 to 1, 1 to 3 somehow. Because really, look. If it was 2 to the 3, right? Like if we had 2 to the power of 3, that would have been 8 minus 1. 2 to the power of 4, 2 times 2 is 4, times 2 is 8. So 2, 4, 8, 16. So this is like a plus 1 minus 1 thing. So maybe we go back to what we saw Thomas say. So let's see if we can figure this out. Well, so you were saying 2 to the this, so 2 to the 0 plus 1 is 1 equals 2. And then we subtract 1 from it. Minus 1 gets us 1. Yes. So if n is depth, then it would be, yeah, so that, yeah, we're going back to what you were saying before. So now if we do 2 to the 2, 2 to the 1 plus 1, which is 2, equals 4, minus 1 gets us to 3. Looking pretty good. 2 to the 2 plus 1 is 3. That gets us 8. And then if we subtract 1 from it, that gets us 7. It looks pretty good. 2 to the 4 is definitely 16 minus 1. 2 to the 5, 32. Ah, look at that. It looks like that might be the relationship here. So look at that. You were right all along. But we just had to treat it as depth. So typically we would say like, well, the relationship between depth and n is going to be like well, from here it's 2 to the power of, and if we were to go this way, it's going to be log 2. Plus the fact like plus 1 minus 1 stuff. Isn't that fun? So, binary tree. What might we want to do with our binary tree? Well, I can imagine like any of the other collections we've used, we might want to add elements, but where? We might want to remove elements, but from where? And we might want to ask if the tree is empty, and that's easy. And we can ask the size of a tree. Maybe that's easy. And we're probably going to want some traversals like we just talked about. But, you know, it's difficult to have a general purpose add, right? Because we might not know where to put things. If I say, okay, add this element to the tree, where should it go? But we will look at binary search trees soon, and there is an answer to that question. And it's also difficult for remove because we might not know where we want to remove from. You know, if I say like, okay, remove E, okay, I guess I'm gonna have to like search for the E and then remove it. But like, what happens if I try to say, okay, remove B? Well, now what? We just removed an interior node. A went to B and then B had 2 children. Like what, like, does one of these get promoted or something to A's left child? I don't know. So there's a lot of things we might want to do. For simplicity, we have like our remove left subtree, remove right subtree, remove all elements. We can check, is it empty? What's the size? We can see if like the tree contains a particular element. We might be able to do like a find. So like contains will be like the Boolean version of find where find actually returns a pointer to it. And then we could have our different traversals like in order, pre-order, and post-order. But I think this is where I'm going to call it for today, because then on Friday, we'll be able to go into the details about how we might actually want to implement these things. Anyways, for the 16 of us that are here, good job. See you later.